Well, hello, good day or good evening all. This is Joe Kraft. I'm calling in from Denver, Colorado, where it's still Thursday night and it is still winter. It's fantastic for me to be a part of this. I wanted to thank Datamine Software for putting everything together, my colleagues and friends there. Likewise, thanks to everyone who's participating today, either virtually or in person. Today I'm going to share some observations on applications of Minemax Scheduler in strategic planning. For a little context before I start, Minemax is native to Australia, so many of you know who we are and what we're about. But for those of you not as familiar, Minemax is a mining software company, and we've been at the forefront of mine schedule optimization technology now for over 25 years. We have solutions in place around the globe, and we've got a small but talented team of software developers and mine planning engineers that really thrive on solving difficult problems in this domain. Last year, we started a new chapter in our company history when we became a part of Constellation Software, and this is a great development for our company and for our customers as it has brought Minemax and Datamine together under a common company. We have already started working on some very interesting things as a group, and we see significant potential for our combined technology and expertise in this particular field, in the field of strategic mine planning. In this presentation, I'm going to be referring to a range of techniques that employ our flagship product, that's Minemax Scheduler Professional. Scheduler is a premium software. It can be used to leverage multiple aspects of an operation simultaneously, and it delivers maximum NPV. And it does this in a way that provides the mine planner tremendous flexibility, and even more importantly, a strong set of controls. And that is because we believe in balancing the power of optimization, right? The power of that mathematical objective with the expertise of that individual mine planner in their own context to steer that schedule in the right direction. Mine planners are doing amazing things with Minemax Scheduler all around the globe. You've heard about some of this already today. You might hear about more of it later this afternoon. I've had the honor to work with a number of our clients personally, many of them here in the Americas. And while each situation is unique in terms of requirements, most mine planners that we talk to are considering core elements or core processes in their strategic mine planning. And they consider that as part of standard practice. Right? So just to elaborate on that a bit further, we're talking about these types of things. Scheduling, considering the time value of money, right? The importance of a discount rate in the context of a schedule. The derivation or the determination of the mining sequence, considering an economic model, right? That's activity-based costing, maybe fixed costing, revenue models, these things. The management of blending, product spec, and destination at the same time the mining schedule is produced. Honoring multiple parallel constraints aligned to production capacities or other practical controls. And solving schedules considering future implication. And what I mean by that is multi-period solving, considering everything that the decisions I make in this period may impact in the future. So I'm going to build upon this, this foundation by talking about some complexities on which that foundation can be used as a platform. Some of those complexities are these: how to incorporate the option for backfilling exhausted pits with waste material in the schedule, how to consider constraints not only on the destinations for blocks, but also on the routes that we use for haulage to access them. How do we include the scheduling of waste for tailings dam modeling requirements, right, to build the dams with mine waste material? How to properly assess capital options in the framework of a mining schedule, and how to incorporate financial objectives into the scheduling process. And I've pulled these 5 out is because we're talking to a lot of people all the time, and these 5 seem to come up fairly often. They're widely applicable, and each of these particular situations presents a unique opportunity to influence the mining schedule. And so in integrated optimization, these are great problems. Let's start out with the pit backfill. So in the pit backfill, I'm referring to a multi-pit or multi-phase environment, which has been designed to allow for the potential of mine waste material from one pit phase to be placed into the void of another once it's been exhausted, right? This is a sequencing-dependent interaction. So in other words, we don't know when a given pit phase is going to be mined out until we schedule. We have a significant opportunity to improve the overall plan by solving the destination for waste at the same time we solve the mining sequence, because it may change that mining sequence as a function of these new dumping alternatives. The haulage differential is going to be one of the greater incentives here for pit backfill, right, from a cost perspective. And so reducing truck hour burden and giving the visibility of that option to the optimizer to be considered during scheduling is a big piece of how we solve this. As you all know, the accuracy of the information we use to populate that optimization model is going to determine the accuracy of your result every time. Right? In terms of the haulage model, we have to decompose the route network to inform the solver of all options for cycle time burden. Likewise, in that same optimization model, we have to define the precedence relationships between mining locations and a dump location that is effectively the mined void of that pit, so that we can control the release of that dumping capacity. The dumping volume is linked to the mining volume through a capacity balance. Then we solve the problem. And optimization is going to consider the benefit of opening up dumping space through sequencing changes, balancing known surface waste dumps with possible backfill locations, considering the impact on haulage at an accurate level, and it will arrive at the best sequence in terms of NPV. Moving on, the next one that I want to talk about is planning for constrained haulage routes. So when we're generating a mining schedule that seeks maximum value, you're going to see schedules pursuing a reduced waste haulage cost whenever possible, right? The last example is an ideal one for that. And this is correct. However, we also need to understand how the cost is being reduced. Automated scheduling tools are going to place material on the shortest routes possible, right? Because we're going to try to lower that cost. However, in some cases, we have to also be aware that we may exceed the material carry capacity route on those routes in any given period as a function of traffic or other limitation, right? The mining location may be able to produce it, the destination may be able to accept it, but while the route that connects those two, can that carry it? That's a different problem, right? So if we're to do it separately, if we were to think about doing a schedule without considering that route constraint when we know it exists, we have a problem, right? Because we have to go in and change the trucking allocations after the schedule has been produced. This is a manual process. It's really painstaking and it's error prone, and it's always going to leave some value on the table because your haulage plan and the sequence that you have set are completely arrived at effectively in isolation. So this is the problem. One of the ways that we can approach that a little differently to avoid this problem is to, within the mine schedule itself, to model haulage routes as process-based decisions. So what that means is for waste, the decision becomes not only what waste dump do I place the material on, but what route do I take to get it there, right? It's a combination. A constraint can then be placed on each route that represents the total available carry capacity on that route. That could be in tons per day, grossed up to be the amount of total tons that can travel on that particular process route in a given period. And you can vary those period to period. And that route constraint on individual routes in parallel with the total available fleet constraint expressed in total truck hours will control the feasible solution space. So those two will operate in parallel. As a result, you're going to see that your shortest route options are going to be filled up to the constraint limit. Remaining material will be scheduled against alternative, less desirable routes, provided it's profitable to do so. And your MPV may be lower as a function of this. But your plan is achievable and your schedule makes sense. All right, another one on waste. This one is delivering waste out to build tailings dams. So, contrary to some popular opinions, the tailings aspect does have implication for the mining schedule. So it's not these two silos after all, right? Generally, certain types of waste are required. All right, geologically, the material spec that's required for building a tailings dam may not be available throughout the pit all the time and not readily available in the mining phases. So we cannot have on-demand delivery and still achieve all of the production things that we want to do. And so to keep costs down, we also want to try to reduce the amount of stockpiling and rehandling as much as possible to fulfill that obligation and our others. We must also ensure that the revenue production, which is tied to the mill, right, and therefore the production of tailings, which is creating this requirement, is not impacted by any delay on the construction of the new tailings dams. Right? This is all interrelated, as you can see. So by solving this material delivery for tailings dam construction, at the same time the mining sequence is generated, we could take advantage of some opportunities, right? We can establish the link between the requirements, the source, and the delivery, and we can reduce the amount of stockpiling as much as possible. So we would model this as an integrated problem. The mill is going to produce tailings at a variable rate depending on what it is fed, and that will influence the tailings dam requirements. So we're already back into this mining sequence problem. The volume of the dam, the volume that's required to build the dam, and the connection from that to the tailings capacity it's going to provide when it's done being constructed is directly linked. It's directly linked also through process and precedence relationships, either on the location side or on the material decision side. Then we populate cycle time burdens for the various routes, giving the solver the differential information it needs to make decisions, right? Similar to how we decompose the routes in the backfill example or the route example. So in this way, the mining schedule can be determined with full knowledge of those interrelated elements, taking advantage of sequencing and destination decisions as it encounters material in the pit with possible mining sequence changes in order to meet these objectives, keeping the mill full if it's profitable to do so, and of course, keeping those tailings dams built on schedule. All right, the next one is Capex optimization. In order to talk about Capex optimization, I find it's always important to start by discussing constraints, because in the way we approach Capex optimization, this is the backbone on which it operates. So in any operation, there are some hard constraints. Generally, these are binding in most, if not all, periods, and those bigger ones are tied to heavy infrastructure or capital, right? There are also other constraints that are operating. They could be, equipment capacity, permitting, land access, location availability, all of those things. So we're dealing with a multiple parallel constraint problem. But individually speaking, Capex optimization is a way to determine whether to invest capital in order to release a certain infrastructure constraint up to a given magnitude. Right? It solves for if, when, and how many instances of a given capital option should be exercised with the aim of increasing project net present value. So when combined with the remainder of the other scheduling decisions and the foundation that we've discussed, and possibly some of these other more complex situations, this type of optimization of the capital element can more adequately inform business strategy. So let's take an example. A common one in the mining environment is a truck purchase. Right? To model this, I'm just going to break it down for you. It's not going to get that technical. We're going to have truck hour burdens, so cycle times for all possible destination combinations, modeled as processes, and possibly route options as well. We need to know the network and the possible burdens for truck hours, depending on where material could go. Then we need to define the total fleet constraint in terms of truck hours per period. So this is your existing truck capacity based on the trucks you have on site, not the ones that you want to buy, right? For the ones that you want to buy or you want to give the option of buying, we develop Capex definitions. And each of these is created in a scenario, and it represents the detail on that asset investment, right? The obvious stuff, the purchase price for the new truck, and the amount of truck hours that asset will provide to the operation, and an assumed use of availability. We can go a little further and get more detailed and model the truck lifespan as well. We can model that with expansion and decay, and it's all on the basis of that capacity, that truck hour capacity. So from a commissioning perspective, there may be a lag between the point that I invest my capital until when my truck is ready and commissioned to hit the first shift, right? And we can represent that on a period basis with a lag or an expansion as it gets going. Likewise, on the tail end of its life, we can also represent a decay or a deterioration of that asset as it ages as a function of how many hours it will provide to the fleet. All right? The capacity expansion in general is effectively an option to release the total fleet constraint limited by the magnitude of the definitions in those capital options, durations, and instances. So armed with that detailed information and this detailed options model, Scheduler is going to determine the number of trucks to buy, when to buy them, as it's determining the schedule. Right? So it will only do this if it returns greater value for the project. And so it is a more coherent way to develop your capital plan along with your mining schedule. And lastly, corporate financial objectives. You know, these vary for each company mining situation. Common examples could be maintaining a minimum cash reserve, maybe repaying a debt by a certain date, maybe limiting capital spending, maybe ensuring a return. Each of these are very different than a straight maximum NPV objective. You won't arrive at those naturally just by seeking maximum NPV for probably all the reasons that you know. All right? In Scheduler, in order to deliver on these kind of objectives, we treat these things as financial constraints. They can be expressed as minimums, as maximums, as cumulatives, right? And there could be multiple parallel financial constraints. A couple of examples, right? For instance, to maintain a minimum cash flow in a mining schedule, the planner can impose a minimum profit constraint. It can vary over time. This will alter the schedule when you go to solve, as it will change the capital or the waste stripping strategy, for instance, in order to return a feasible schedule, especially those who have major stripping hurdles. Or the planner may have a range of possible equipment purchase options. Maybe it's a greenfield environment and they've got a limited amount of capital that they can deploy. We would impose a Capex maximum constraint, or maybe even a cumulative maximum by a certain date in the periods, to choose the best assemblage of all of those mobile fleet unit options in order to stay within your budget. So in general, the financial constraints in combination with your other general ones, those based on mining capacity, benches mined per period, process capacity, blending, locations, right, will further control that optimization. We talked about control, and that's what this is all about. And if you have set it up properly, this approach will deliver a mining schedule that's practical to execute, that honors those financial prerequisites and returns maximum value for the business. And that captures it. Thanks very much, everyone.